Right, I think we'll start. Hello and welcome everybody. Thanks a lot for joining today. My name is Jakob Heiden. I am an application engineer at IRsweep and I'll be hosting today's webinar. The webinar today will be the third one that we will have that is devoted completely to the high spectral resolution that you can achieve with Quantum Cascade Laser Dual-Comb spectroscopy. And actually for me it is a back-to-back event with a very nice event that we had yesterday at the University of Namur. There we had an inauguration, a scientific day that celebrated the inauguration of the first IRsF1 that we installed in the lab of Muriel Lepere. And this is IRsF1 that is in the high-resolution step-sweep mode that I will talk about after that. And the talks that were given yesterday together with, and it was a nice work that was shown there, and the nice work that was cited here on this first slide really shows to me the momentum I think that is right now in this kind of research. So I'm really happy to host today Kenichi Komagata and Michiel Janella to have them here. So hello to the two of you. Hi.
Hello everyone.
Hi everyone.
So a brief outline of what you will hear today. I will continue talking for maybe 9 more minutes and give you an introduction to the high resolution options of the IRsF1 spectrometer of IRsweep. I will then hand over to Michele, who will talk about the developments of dual-comb spectroscopy with frequency-swept quantum cascade lasers at EMPA. And finally, Kenichi will talk about how they managed to achieve this very impressive frequency accuracy in those measurements below 1 MHz. Finally, there will be a Q&A session. So please there should be a questions box, I think, on the bottom of your screen. Use that to raise questions already during the talk. We will answer them in this Q&A session. I start with a brief introduction to dual-comb spectroscopy. In dual-comb spectroscopy, you use 2 frequency combs, laser sources, and those are laser sources that don't emit at a single frequency, but over a broad spectrum, and within this broad spectrum, they emit at well-defined lines that are equally spaced along the wave number axis. And we choose 2 such lasers where the spacing between these lines, so the repetition frequency, is slightly different. And what that means is that when we overlap them on a detector, the lines that are of line of one laser will always meet with a nearby line of the other laser, and they will create an interference and a beating frequency that is in the radio frequency domain, in the radio frequency range. So you can detect this directly on your detector signal. And since this difference is different for each optical line, it means that your optical spectrum is completely mapped onto your radio frequency spectrum that you can detect on your detector. And this has several advantages. The one that we exploited the most so far is probably the high speed that you can achieve. So you get the complete spectrum over, for example, 60 or more wave numbers in as little as 1 microsecond. The advantage that we will talk about more today is the high spectral resolution. And before we can talk about that, I would like to briefly, I think it's necessary to talk about 3 terms with that respect. The first is the term resolution. And what I mean by resolution, I think is basically it's the ability to resolve a very narrow spectral feature and a very narrow absorption feature of your sample. This is limited in our case by the width of an individual comb line, and the width of it, that's actually not so easy to measure. What we do know is that it's certainly better than 3 MHz, so 10 to the minus 4 inverse centimeter. Probably it's actually quite a bit better. The sampling, it means at which frequency along your wave number axis do you actually have a comb line, and can you take a measurement. And in a normal measurement mode, this is given by the repetition frequency of the lasers, which in the QCL case is typically around 10 GHz. So every 0.3 wave numbers, you have 1 line. The third term is the accuracy. So the accuracy means how well can you assign a wave number, an exact wave number, to the transmission measurements that you took to each line. One example, talking about resolution, is shown here on the bottom right that I want to highlight. So here you see an absorption line that was measured in the group of Frederick Merck at ETH Zurich in a cold jet that has only a half width, half maximum that is on the order of 2 × 10⁻⁴ inverse centimeters. That really highlights basically what I said here. The resolution really is excellent with these spectrometers. The sampling, basically, if you want to do a high resolution spectroscopy, usually has to be improved, because otherwise you have a very high chance of missing all the absorption lines that fall between two emission lines of the comb. The way you can do this, luckily, you can tune the frequency of QCLs via temperature or via current. So what you have to do is just increase the current stepwise or continuously and measure continuously to derive a full spectrum. The question then arises, of course, how do you know for each measurement where exactly on the frequency axis you are? How do you know the frequency at each step? And before I pass on that question to Michele, I will briefly talk about the solution that is implemented in the IRsweep 1, which is what we call the step sweeping technique. So in a step sweeping technique, basically the key idea is that we change not both laser currents at the same time, but that we change only one at a time, meaning that for every step, you can use the other laser as a reference because it didn't change relative to the first step. And you can then measure the difference between the step that you did in the optical domain directly on your radio frequency signal. This is, of course, a very short description. The key advantage is that you get a quite accurate wave number axis, as I will show you in a second, and that basically this is what you get from the instrument, kind of out of the box without any additional instrumentation needed. If you want to know more about it, I recommend you go to our homepage and watch the webinar that was given by Professor Muriel Lepere on demand. I would like to briefly share with you some, I think, quite impressive data that came out of the group of Professor Muriel Lepere that was published just 2 weeks ago, where they characterized the accuracy that they achieve with that measurement technique. And what they did is they compared a measurement of N2O with a height run reference. So they compared the line positions that they found with the listed ones. And what you see here is this plot on the top right. The error of the lines was within 4 MHz, so 10⁻⁴ inverse centimeter on that word. A second test that they did is they did a measurement of methane at very low pressure. So the lines are Doppler limited. So you know the width and the profile of the lines very well. And this known line width are the red stars here in this graph. And the gray dots are the found line widths. And you see that what is remarkable about it is that the found values really scatter all around it. And that's a key difference to, for example, FTIR, because if the resolution of the instrument was larger than 2 MHz, for example, larger than its residuals, it would mean that all the found values would be above the predicted values, not scattered around 0. So this shows that the instrument response function of the spectrometer really is very, very small. With that, I'm already at the end of my part of the talk. I would like to briefly introduce my guest speakers before handing over to them. So Michele Gianella graduated from ETH Zurich in physics in 2006. He then defended his PhD thesis that he did in the group of Professor Markus Siegrist, also at ETH Zurich, where he worked on infrared laser spectroscopy applied to gas phase analysis. from 2011 to 2012, he continued at ETH Zurich as a postdoc in the same group, and then moved on to Oxford to the group of Professor Grant Ritchie, where he was a postdoc and also a Marie Curie fellow. He then returned to EMPA, to Switzerland, where he joined the group of Professor Lukas Emmenegger at EMPA until, where he still is right now. And I'm very happy that he will join IRsweep as a colleague of mine very soon. Kenichi Komagata, he finished his master also in physics at EPFL in Lausanne in Switzerland in 2019, where he did research on silicon nitride microresonators in the group of Professor Tobias Kippenberg. And in 2019, he started his PhD studies at the Université de Neuchâtel in the group of Professor Thomas Südmeier, where he works on the stabilization of quantum cascade laser frequency combs and all things related to very high frequency accuracy and QCL frequency combs. With that, I would like to ask Michele to share his screen and take over, please.
Okay, I'll just kick you out then.
Yes.
Okay.
Thank you.
There. Perfect. Let me just. Okay. Hi everyone, and thank you, Jakob and IRsweep, for hosting us. The work we present today has contributions from quite a large number of people. Myself and my colleagues at EMPA in the laser spectroscopy group of Lukas Emmenegger, our colleagues in the group of Jérôme Feist at ETH Zurich, Kenichi and others from the time frequency lab of Thomas Südmeier at the University of Neuchâtel. And we have received a lot of support from various people at IRsweep over the years. So in frequency comb spectroscopy, we use an optical frequency comb to probe a sample, and then we need some means by which to measure the attenuation and possibly the phase shift that each of the comb teeth experiences. And there are multiple schemes for this, but with QCL frequency combs, the most common one is the dual-comb scheme that's shown here. So it involves using a second comb with a slightly detuned repetition frequency, and it is used as a local oscillator. And when we overlay the two beams on a detector, this generates an interferogram, which consists of a superposition of evenly spaced beat nodes, and whose radio frequency spectrum may look something like this. And then if a sample is present on the path of the interrogating comb, then the teeth of the interrogating comb are attenuated and phase shifted by the sample's absorption and dispersion. And these two effects are measurable on respectively the magnitude and the phase of the detected beat nodes. And what I want to emphasize here is that, well, the point spacing of the spectrum is the repetition frequency of the interrogating comb. So this is the situation on the left, where we have a sample transmission, and this is sampled every FRIP. And with dual-comb spectroscopy, we can achieve very fast temporal resolution of the order of the reciprocal of delta FRIP, which is the beat node spacing. So this is typically a few microseconds. And again, the spectral point spacing is given by the repetition frequency of the interrogating comb. But if the spectral features are narrower than the spacing, then we end up undersampling the spectrum. However, luckily QCLs and QCL frequency combs can be tuned very easily. We can change their emission spectrum by changing the temperature or the current, and therefore a large number of spectra can be acquired by with increasing offsets of the interrogating comb, and then the spectra can be in the second step interleaved. In 2018, 2019, we started with this instrument with an IRIS F1. The optical layout was the so-called phase-sensitive configuration, where the sample is probed only by one of the combs. This is a requirement for high resolution spectroscopy. And the other feature of interest is that, and this our main contribution was that we modulated the currents of the two combs to offset the spectrum, and then we interleaved the acquired spectra. And with this, we obtained the first high resolution and gapless spectra measured with a slightly modified IRIS F1. So for this demonstration, we used methane. And depending on the sweep duration, we interleaved up to 30,000 spectra, which gives us a point spacing of approximately 300 kilohertz. Much more recently, we measured mixtures containing ethylene, acetylene, propylene, and methane. And as you can see, this is a much more congested spectrum. And what we wanted to see here is if we can measure the amount fractions accurately, and it's looking good so far, but it's still a work in progress. Now, what we learned here from these measurements is that there is a bit of a challenge in how to interleave the spectra correctly. How do you know at each instant of the sweep, so during these 120 milliseconds, for example, how do you know at what frequencies the comb teeth of the interrogating comb are? How do you know at what frequencies you are probing the sample? Now, we know these frequencies depend on the laser current, but how exactly, and is the relationship repeatable? And the repetition frequency as well, it depends on the laser current. So it's not a rigid sampling grid that is being swept along, but the grid itself compresses and stretches during the sweep. So the figure here on the right shows in a cartoon form what happens to the comb line frequencies during a sweep. So as the laser current changes, all the comb lines shift. Here the current decreases and the comb lines go up in frequency. This is determined experimentally, and it's the same behavior as for the distributed feedback QCLs. And the shaded areas represent the spectral regions that have been covered or are swept over by the various comb teeth. So at all instants of the sweep, the comb lines are evenly spaced because the source is a frequency comb, but the spacing, as I said before, is not constant throughout the sweep. And the idea here is to measure the frequency of one comb line versus time by using a distributed feedback laser. And this will be locked to some molecular transition, so it has a constant and a known frequency. And then we detect the beat node between this laser and one of the comb lines, and we give this comb line the index 0. And by measuring this beat frequency and by knowing the frequency of the DFB laser, we can then compute nu zero versus time. That's the comb line frequency. The repetition frequency, this is always easier to measure. It can be measured optically, but in QCL frequency combs, it can be measured electrically too. So the modes that beat within the waveguide section of the QCL within the chip, they create a time-dependent population inversion grating, and this generates a modulation of the laser voltage, and this modulation is exactly at the frequency FREP. In this example, this has been used in this way. So the repetition frequency has been extracted with the bias T, and then it's been shifted by a known and a constant amount. And then it has been injected into a second comb, and this way the repetition frequency difference was kept not only constant but with a known value. And remember, this is the beat note spacing. Okay, but if you attach electrical wiring, additional electrical components to a laser, there's always the risk of having additional problems such as ground loops and so on. So alternatively, this intermode beat can be detected by aiming a microwave antenna, horn antenna, to the housing containing the interrogating comb, and then all you need to do is to apply sufficient amplification, and the intermode beat can be detected without any additional galvanic connections. So to implement this referencing scheme, where the comb is referenced to a locked DFB laser, we moved from this instrument to, well, to this. So here is the laser module with the two laser housings for the interrogating comb and the local oscillator. It's on an IRIS core. It's a sort of a docking station for these laser modules that fit into the IRIS F1 instrument. This photo was taken while we were still using cable and DC blocks to measure the intermode beat, so there's no antenna in this photograph. And then we had a multipass cell, a 36-meter multipass cell. This is a commercial cell from Aerodyne. This is where the sample compartment would be in the original instrument. The two photodetectors are at the back. Then we have the reference laser is hidden here behind this aluminum profile. The reference cell has a small amount of nitrous oxide, and the laser is locked to one of the transitions. The corresponding detector is here at the back. And then we have a fourth detector in the setup on which the interrogating comb and the DFB reference laser are heterodyned for the comb 2 frequency measurement. So in red is the interrogating beam. So it's a phase-sensitive setup configuration. Only the interrogating beam goes through the sample. The orange is the local oscillator, and the blue is the reference laser. And here you see it's overlaid with the interrogating comb. With this photo, I'm going to hand over to Kenichi, who will give you the details on how exactly we achieve this relatively accurate frequency scale as promised in the title.
Kenichi, can you share your screen?
Yeah.
Perfect.
Thank you, Jakob, and for the introduction and for hosting this event, and thank you, Michele, for presenting and introducing. So yes, as Michele told you earlier, we want to know the frequency of each comb line of the interrogating comb. And for that, we need to know the frequency of one comb line, U0, and the repetition frequency. The repetition frequency is relatively easy to measure, as I told you. But for the comb line, so there's a few challenges. First, so actually the beat note is going to span half the repetition rate of the comb, and for QCLs, this is in a few gigahertz, and in our case it was 10 gigahertz. So you need this beat note will span up to 5 gigahertz, and you need to be able to process it over this range. And also the commercial photodiodes that you can get are usually limited to 1.2 gigahertz in bandwidth, or that's what's specified. And the third challenge was to obtain a high accuracy reference laser. So to establish the reference laser, so we used I developed a method that we published elsewhere. And we use this method, and I'm going to introduce it. And for the processing of the beat node, we based ourselves on the marker method that was proposed by Delhay and co-authors in 2009, and we adapted it for COM-swept measurements. But I'm going to go in details over these two steps. So as for the reference laser, so we want to lock on a known molecular transition of N2O, which has been measured accurately with accuracies on the order of 70 kilohertz. And so we applied a modulation to the laser, and then we at about 40 megahertz, and then we demodulated the signal in order to obtain a wavelength modulation signal, so which is shown here. And then we have a nice error signal where we can lock to here, which corresponds more or less to the center of the transition. And yes, in this work, we have an accuracy on the order of 180 kilohertz, which is small compared to the Doppler width of the transition. Yeah, as for the marker method, so here's the original paper where they suggested it. So the idea is to use a frequency comb to calibrate a scanning CW laser. So in their case, they wanted to measure the dispersion of the alpha micro resonator. So I'll put the laser pointer. So they would beat an external cavity diode laser with a frequency comb, and then each time the beat node between the comb and the CW laser is goes in at the frequency of a bandpass filter, then you get a signal. And actually, so each time here represented in function of time the frequency of the beat node of the laser actually. Sorry, each time the laser crosses one comb line represented as horizontal lines. Then you would get a marker because, for example, if this bandpass filter is at 20 megahertz, so you get a marker when the beat node is at minus 20 megahertz, and then when it's at 20 megahertz, and then you assess that the diode laser was at the frequency of the comb line just in between the two markers. And then by having additional filters and an additional channel, then you have more independent measurements, so you're more robust against noise. And this was used, for example, also for comb-calibrated spectroscopy. But in our case, we're doing something different. We're keeping the CW laser fixed, and we're scanning the comb. So that means that actually over the scan over one free spectral range, over one repetition rate, then you will only get one marker. You see the beat node between the two will be near zero only once. So this is not very useful. So what we do, we mix the beat node, so between the reference laser and the comb, with a RF frequency comb. So which is generated by sending a frequency on some nonlinear device, which just generates harmonics of it. So you have a harmonic comb. So there is a signal at every 475 megahertz in this case, which you can tune it. So that what happens when you mix this beat node against this, we called it a synthetic comb, then you get a marker each time, every 475 megahertz. Yeah. And then we put the bandpass filters And as a last step, actually, we use logarithmic amplifiers, which which actually increase the dynamic range. Actually, they make the dynamic range logarithmic, so that we can cope with the varying signal strength when you go from 1 gigahertz to 5 gigahertz offset, and when the 3 dB bandwidth of the photodiode is 1.2 gigahertz. Yeah, and then we can get these markers. So here's the original beat node. So it's when the beat node is at 0, so near where the comb line is near the frequency of the reference laser, and then all the other ones result from the beating or from the mixing with the radio frequency comb. Yeah, and here's a picture of the implementation. So you have here it's the comb generator, and the signal from the photodiode comes from here. So you see that it's a little bit complex. I'm not an expert into electronics, but in principle, you could optimize it into one single PCB. Here we just use the off-the-shelf components, mostly from mini circuits. And I would like to thank Silent System for providing the low noise power supply that was used to power all the low noise amplifiers. Yeah, and also we also used equalizers, which basically attenuate the low frequency components of the signal and don't attenuate the high frequency part in order to reduce the imbalances of strength. And also we split the signal between a low frequency branch and a high frequency branch also, so that we can adapt the gain between the two. Yes, and this allowed us to, so we got this, all these markers. So this is from a sweep over a little bit more than FSR. And from this, we can deduce as a function of time the frequency of a comb line. Actually, we are, if we remove the linear trend, we see that we are actually measuring 2 comb lines. And we also see that it's easy to detect like noise or some other signals or from spurious peaks. And if we fit it with a 10th order polynomial, then we have residuals on the order of 250 kilohertz of RMS. And for FREP here, I won't go into detail, but we can measure how it changes over time, and we also get we get a residual for about 2.5 kilohertz. What we did first, we measured N2O, which, as I said earlier, has been measured accurately and by other groups, and we compared the transition centers that we get with this with the literature, and we got good correspondence. Also, our error bars show that actually in this dark gray region we have an accuracy better than 600 kilohertz, whereas the light gray region is better than 2 megahertz. We also saw that there was some small biases, like 180 kilohertz and 2 on the offset and 3 kilohertz on the repetition frequency. Yeah, and here and then we can use we can use the calibration spectra to remove these biases, and we considered these uncertainties here in terms of SNR. The uncertainty was better than 300 kilohertz. The uncertainty coming from the fit and so. No. We also compared how can we tune the acquisition speed, so the time of the tuning of the sweep. And the fastest that we could tune continuously was in 27 milliseconds, and the slowest in 215 milliseconds. We could have tuned slower, but we need then to improve the buffer in the acquisition. And for faster sweeps, actually, it becomes discontinuous, and we believe that it's due to back reflections, because the laser dynamics are supposed to be very fast. And yeah, there's a trade-off between acquisition speed and precision, which is expected. And the good thing is that there's no bias that changes due to the varying speed. As an application, we measured methane, and this allowed us to get better accuracy than published literature. Although now we expect that another group, the group of Alexandra Potinovic, will publish their results very soon. And yeah, as before, we got accuracies for the best ones on the order 600 kilohertz, and for most of them better than 2 megahertz. Yeah. So as a conclusion, we developed a R-square scheme for swept cones, and we could then demonstrate a fast mid-infrared spectrometer with a very high frequency accuracy, and we did a spectroscopy of N2O and CH4. As an outlook, well, this allows us now that we have a very robust frequency scale to measure complex molecular mixtures where we're not sure what line, where otherwise we wouldn't be sure what transition corresponds to which molecule. We can also study molecular line shapes. And also this scheme actually could be adapted to do the opposite, that is to use a QCL comb to reference, and for example, an external cavity QCL which scans. And also we could adapt this scheme to other integrated comb sources. So with this, I would like to thank you for your attention and acknowledge our support and partners.
Okay, thanks, Kenichi. With that, the Q&A session is open. So please make use of the questions feature in Zoom. Maybe I can start with a question to both of you. I suppose you showed methane, that you can apparently improve the line list for methane. Is there what kind of measurements are maybe ongoing, or which gases would you target to? I suppose you can get quite a number of better line lists for many gases, right?
Yes, of course. I mean, you see for N2O in that measurement, the emission spectrum of the module fits more or less perfectly. You have many lines of both branches, and the same applies to some of the new 4-band of methane, I think it is. Well, yeah, no, I think it's really a question of what can you measure, what lies within that wavelength range that you have available.
Then, since there's no follow-up question yet, then how easy is it to adapt to the next wavelength range?
Yeah, I wanted to say that in principle, if you have another module, you need a DFB, and you need a transition that is known, or you can also do a nonlinear conversion, and then you can adapt this scheme. It's yeah.
So you can probably, so if you would have a second module that overlaps spectrally with the first somewhere, then you can basically probably use the accuracy that you just measured on one line, right? For the next spectral region, let's move forward.
Yeah.
From there. Okay. I think there's a question. So what's okay? If you would, so in your first implementation, so without the DFB-Q cell and beating with the DFB-Q cell, what limits the accuracy to which you can determine your wave number axis if you just sweep the lasers freely?
Without using the reference laser?
Yes.
Well, so what we originally did was to say, well, you take a sample with as many lines as possible, and if you know where they are, you can then make, since it's a frequency comb, you know that at every instant you only have two frequencies you need to know, the repetition and the and an offset frequency. And in principle, the repetition, as you've seen, you can measure it, so there's only really one. And you could then kind of make a model that says, okay, I need the model predicts the frequency of every comb line at every instant of the sweep, and if I know at what instant of the sweep which comb line measures which absorption line, and I know the center frequency of that line, then you can compute you can compute some parameters that gives you the frequencies of all comb lines at every instant of the sweep. And in this first, when we published the first result with methane, I think that the accuracy is well, accuracy is hard to say because we compared with Hydran, so that's not that accurate either. But the precision is of the order of 30 megahertz. Let's say plus minus 15, plus minus 20, and this is probably I think this is a very convenient. It's not, I think, as elegant, but of course you don't need anything, any additional hardware. I mean, you need a reference cell, and then you periodically put it in the beam and you recalibrate your axis. But there's another thing that could be done, and this really relies on if you could have a photo detector that is fast enough, and there is at least one quantum cascade detector that should in principle achieve 20 gigahertz bandwidth from Hamamatsu, I think. You could in principle keep your local oscillator comb fixed and just sweep the interrogating comb, and this would just move your beat nodes. And this is similar to what you do in your step sweep, right? You keep one fixed, and that's your reference, and you measure relative to that. And then you only have one degree of freedom, but it's just one number. You just need to offset this scale so that it matches, and that of course would be very nice. But you need a 10, 15, 20 gigahertz bandwidth detector, and you pay for it in terms of noise.
Thanks. There's one comment here that I may read out from Muriel Lepere, saying, probably encouraging what we also encourage. She says, great results. If you are looking for modules, I have to. This is so we go ahead and exchange modules, and so yeah, these results open up real possibilities for improving our knowledge of the possibilities of many species. There's another question to Michele. Michele, thanks for the excellent presentation. Have you applied your system to samples with unknown composition?
Hi, Marcus. Well, not exactly. I mean, the results I've shown, the ones that we've done recently with the acetylene, ethylene, propylene, methane, the idea is that would be the case there. I mean, at the moment we have we have trained the system, if I can call it that, to verify that for the measurements that we have, for the samples that we have, which have a known concentration, that the predicted concentrations fit. But this would be, it could be done. We could now, in principle, measure an unknown sample and try to determine the concentrations of the components. At the moment, all we have is really, I think, a validation that Jakob did, and this plot I showed that looks very, very good. But of course, we have to increase a bit the statistic, take a few more measurements.
Yeah, so this is a cross validation in this case.
Yeah.
Leave one out. There's one more question. I don't know if you want to answer it, Michele. How does the resolution compare to high resolution Fourier transform infrared spectrometers?
Well, the resolution is the width of the comb lines, and I mean, we usually say that this should be below a megahertz on the time scale on which the measurements are taken. We haven't actually measured it because it's with this rapid sweeping, it's it's quite difficult. But it's well, you've measured it in step sweep, and you have let's say it's probably a couple of megahertz or possibly even less. High resolution FTIR. I think there's a prototype, or there was a prototype that reaches, is it 10-15 megahertz? I don't want to say something wrong, but it's easily better in terms of resolution.
Sure. And much more compact. Much more compact.
Yes, than the high, yeah, of course, yeah.
Okay. If there are no more questions, then I think I will thank thank you again, Michele, and thanks Kenichi for talking today.
Yeah, thank you.
And I will close the webinar.
Mm-hmm.
Many thanks. Have a good weekend.
Yeah.
Goodbye.
Goodbye.
Goodbye.